The source of that magnetism was betrayed years ago, more than 150 years ago, by a fellow by the name of Hans Christian Ørsted, who was a professor type teaching, I believe he was in a high school classroom. And he was showing the students that there's no relationship between magnetism and electricity. The physics books at that time had electricity as one subject and magnetism as another. And Ørsted was showing there's no relationship between the two. And one of the things he would do is he would line up the piece of wire like this and put it over a magnet, pass a current through it, and you really don't see anything happening. There's no interaction. But after class, a student came up and held the wire in this direction, and when a current passed through it, okay, watch this, when a current is passed over the wire like this, boom, you see that interaction? It turns out there is an interaction between a current carrying wire and a magnet. And it turns out, to make a long story short, the source of all magnetism is moving electric charges. And when the charges move through the wire, they set up about the wire a magnetic field. And that magnetic field is in concentric loops around the wire. If I pass this wire through a hole in a piece of paper, and I put a whole lot of little compasses around the wire, and no current goes through, all those compasses would point north. But you know what would happen if I put a current through that wire? All the compasses will line up with the field. And it turns out that field, it takes the shape of concentric circles about the wire. The further away you get, the weaker they get, but the direction is all that way. So surrounding every current carrying wire is a magnetic field that takes the direction of the concentric circles. I want to show you something that's even more interesting than what we've seen. Let's take this magnet. I'm going to put the wire in the magnetic field of this magnet, and I'm going to touch this momentarily so I get a pulse of current. And when I do that, when a current goes through this, would this wire, in a sense, be a magnet? How about when no current goes through it? It's copper wire. Copper is not ferromagnetic. Copper, you've all tried when you were a kid to pick up a penny with a magnet. It doesn't work, does it? Because the penny's copper, okay? So the only way you're going to get magnetism with copper is to have electrons flowing through it. Electrons flowing through anything would set up a magnetic field around that anything, yeah? Let's see what happens with the magnetic field of the wire and the magnetic field of the magnet. Let's see if there's any interaction. What do you suppose? Watch this, gang. You see that jump down? See that jump down? Let me turn the magnet around. Jumps up. Did you see that? I'm going to do it one more time. Watch. Wow, jumped up. So one way it jumps up, and the other way, put it this way, it jumps down. I wonder if that jumping motion could be harnessed. How many people say, well, no, there's probably no practical application of that. Wires will move in magnets. Big deal, right? Is it a big deal? It's a very, very big deal. Because guess what this underlies, gang? Electric what? Begin with M, end with odors. Try it. Motors. Any electric motors be working on such principle, okay? And dig this, whenever you see any electric motor, realize, you know, sometimes we see things and we're so overwhelmed with the complexities, we don't know what the nitty gritty is. Realize the nitty gritty of an electric motor is simply a current carrying wire, boom, being deflected in a magnetic field. Period. That's it.
All right. So yeah, that's like one version of the right-hand rule, isn't it? So let's take a look. We got magnetic field lines here. Those blue lines are magnetic field. That's what B is, right? Magnetic field. Right. And then A stands for area. Notice they're defining the direction of the area as like perpendicular to the plane of the area. Right? We did a similar thing for torque last semester, sort of. Well, AP doesn't really care about it, but right. So this symbol here, I think it's Greek letter phi, right? Represents flux, right? And flux is just magnetic field times area. Well, it's a certain product between those vectors, right? So look at that. When you turn the sideways, right, the flux goes to 0. Okay, so it's really how much magnetic field is going like through some area, right? And then if you turn that area upside down, the flux goes negative, right? Okay, so B times A times cosine of the angle between them. Right? Kind of reminds me of a dot product, right? How about this? What if you went all crazy and had a not like a flat plane area, but like some really warped area? Okay. Well, effectively all that is just like if you were looking head on, like how much area would you see, if it wasn't all like warped like that? And it's just the same thing, same amount of flux, right? And then here they just switch this to calculus notation for, again, if you have like some crazy stuff like that. But you could break this to like 100 tiny squares and do the flux for each one, and then you could aggregate it like that. Now, when you turn that flux on and off, the rate change of that flux is a voltage that is induced. And that's going to lead to this last Paul Hewitt for today. Rate change of flux.
This was done by a couple of physicists about the same time in history. One was Michael Faraday, a Scottish guy in England, and the other was Joseph Henry, an American type in Vermont in the 13 colonies. And they both at the same time found the same effect. And here's what they discovered. They had meters similar to this at that time, but they didn't know how to get electricity. Well, they got electricity from batteries. A fellow by the name of Volta, Alexander Volta, Italian type, made batteries, and that was kind of nice. Everyone was excited about electricity. And Michael Faraday and Joseph Henry discovered the following. No batteries over there again. No batteries, no tricks. Magnet, wire, meter. Watch this. You see anything? No. Faraday didn't see anything either. Okay. And but watch this. Henry didn't see anything either, but watch this. Did you see something? Again. My goodness. My goodness. There's no battery nearby, and guess what we are generating? Begin with EC. Electric current. I am generating electric current. And Faraday and Henry found out that. No batteries, no cells, no lightning, none of that. Just the motion of a wire in a magnetic field. So Faraday goes to bed and he's really excited about that. And while he's in bed that night, I'm making this up now. While he's in bed that night, he's kind of thinking, gee, I wonder what would happen if I did it with 2 wires. So he gets up in the middle of the night, takes his candle, goes downstairs, had to do a candle. Little did he know that he was going to get rid of candles. And the candle industry was furious later on, okay? But what he did is he went down and he took 2 wires. And guess what happens with 2 wires, guys? Twice as much current. Goes back to bed. Then he thinks, I wonder, 3 wires. Shall we try it? Didn't sleep the rest of the night, gang. I wonder, 1,000,000 wires. What do you think? 1,000,000 times as much. Okay, this was a remarkable discovery that one can, it turns out, induce voltage by simply moving a wire in and out of a magnetic field. And so Faraday's discovery is couched a little differently. Today it's called Faraday's law. And what it says is this, a little more complex. Change the magnetic field in a closed conducting loop of wire. That may not be conducting. Just change the magnetic field intensity in a closed loop, and you will induce a voltage in that loop. Now this loop happens to be a copper wire, so the voltage in that produces a current. So look at this, you get a current. Change the magnetic field in 2 loops of that closed copper wire, 2 loops of that circuit, and guess what you get, gang? Twice as much voltage. 3 loops, 3, da, 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 da. So that's the rule. All you got to do is change the magnetic field intensity and you will induce a voltage, which will produce a current if you're talking about a conductor. Ain't that neat? That is really, really nice. Now we can produce electricity. You know how all of Europe started converting to electricity.
Hey, yo. All right, so I'll show you guys the the math of Faraday's law, and then do a demo with this. Okay, so you guys remember that last animation you guys saw? Flux was area times magnetic field, right? And then well times cosine of the angle between. Okay, so like a dot product. Right now, if you turn that flux on and off, that's what this is, right? Delta phi is like a change in flux per change in time. Okay, so rate change of flux, right? Okay, so that's like moving in and out some rate. So you're like say about like a coil of wires, right? Hey, what if this is like spinning over a magnetic field? That flux would be turning on and off at some rate. Okay, every time it turns 90 degrees, it turns off and then turns on again. And then that's what you're showing with like number of loops, right? Number of loops. So if you have like twice the loops or 3 times the loops, you get 2 or 3 times the voltage. The voltage reduced, right? They said if you have like a million wires, you get like a million times the voltage, right? From like this spinning in this magnetic field. Okay, so I'll show you guys that.